So I already discussed the open syscall, which is going to open a file specified by the path name argument with the permission flags of the flags argument. And open is going to return the file descriptor of the new file, or -1 if there's any errors, for example, if the file does not exist. Now close is going to close a file descriptor, and if we look at this example on the previous slide, we see that file descriptors 3 and 4 both point to the same file description. Now, if I close 3, there is still a reference to that file description by the file descriptor 4. So I'm not going to eliminate that file description entry. However, if I close 3 and 4, then there are no more references to that file description, and I can safely remove that file description and free it from memory. Now, read and write have the same signature, except read is going to read up to count bytes from the file descriptor, or the entry corresponding to that file descriptor, into the buffer, and write is going to write from the buffer into that file corresponding to the file descriptor. Now, lseek is something new. lseek is going to reposition the offset of that file description entry based on the offset parameter and on a flag that either calculates the offset based on the current position, so adds or subtracts the offset number from the current position, or we can just specify that we want to calculate the offset from the beginning of the file, which is going to basically reset the position to 0 plus offset instead of current position plus offset. And you'll see an example of that in the next slide if that didn't really make sense. Okay, the last two that we're going to cover are dupe and dupe2. If I pass in dupe to some file descriptor, it's going to allocate a new file descriptor that points to the same file description as the parameter specified. So here, if you imagine in the first table, the reference from file descriptor 4 to that file description did not exist, and I called it dupe3. Now we would allocate file descriptor 4 and point it to the same file description as 3. And that's an example of the dupe syscall. Now, dupe2 is similar, except instead of allocating any file descriptor that's not being used to the old FD, we're going to change the file description that the new FD is pointing to correspond to the file description of old FD. So in this case, we note that 0, 1, and 2 as file descriptors are reserved for standard in, standard out, and standard error in that order. If I were to say dupe2, 3, 1, what that would do is remove the arrow from 1 to standard out to now point from 1 to the file description for a.txt in this diagram. So we are basically redirecting the standard output to the file a.txt. And so when we're trying to print to standard out, it's actually going to write to a.txt instead. Okay, now all of these functions that you just saw are the low-level API, which means that every time we execute one of these functions, we're actually executing a syscall that's going to drop into the kernel and incur that overhead of switching from user to kernel mode. And now if we're using the high-level API, instead of executing a syscall every single time we call the high-level API's version of read or write, we're actually going to check if our user-level buffer is storing any of the data that we need to return to the user. So what does that mean? Basically, the first time that I open a file, fopen, I'm not just allocating a file descriptor for that file, but I'm also going to allocate a user-level buffer that can store data that is being read or written from the file upon these syscalls. And so maybe the first time that I call fread to the file, I'm going to store more data than I actually need to give back to the user in that user level buffer So the next time I call fread, I don't need to execute a syscall, but I can just look in my user level buffer instead and read from that buffer instead of going into the kernel. So you can imagine that this is helpful if I'm continuously calling fread in tiny chunks of bytes that I want to read from the file. And instead of going to the kernel every single time, I just go to my user buffer and I don't have to incur that context switching overhead. Now, we keep in mind that the user level buffer is of a limited size. So if I'm calling fread with the maximum number of bytes that the buffer can store every single time, well, then I'm going to have to go to the kernel every single time. I might as well use the low level read syscall. Okay, so the functions for the high level API are very similar. We have fread, fwrite, which I described previously. We also have fflush, which is new, which is going to force a write of all of the data that's in that user level buffer to the corresponding file. So anything that is stored in the user level buffer is going to immediately go to that file with a call to fflush. Normally, the data will be flushed either on a special character or when the buffer is full, but you can make that happen earlier with a call to fflush. Okay, so what's the difference between fopen and open? I very briefly described this, but fopen is not allocating just a file descriptor, but is allocating this file star opaque type that the user can only interact with through the function call specified here instead of syscalls that directly take in the file descriptor number. So fopen is going to be a high-level API that returns this opaque file star type, which under the hood stores a lock on the user level buffer. This is not accessible to the user themselves. And open is just going to return an integer that is the file descriptor for that file. Okay, now let's look at this example. So what will test.txt look like after this program is run? You may assume read and write fully succeed. Okay, so let's look at what's happening. We allocate a buffer of 200 bytes, and then we set the contents of that buffer to be 200 A's. Now we open a file descriptor for test.txt so that we can execute low-level operations to and from that FD or file descriptor, and we first write from the buffer to the FD, and we write 200 bytes. So we're writing 200 bytes of A's, so 200 A's, to the file test.txt, and then we reset the position in the file. So seek set is going to reset the position of that file descriptor entry starting from the beginning of the file. So if I say I specify an offset of 0 with the flag seek set, I'm resetting the position of my file descriptor entry to be 0 plus 0. The first 0 is indicating that we're resetting it from the top of the file, and we're adding the offset specified in the function call, which in this case is 0. So we're resetting the position for that file descriptor entry to 0, and then we're reading the first 100 bytes back from the file descriptor to the buffer, which means we're reading 100 A's into the buffer. And then we're seeking again. This time, note that we're using the seek cur flag, which means we're going to reposition our position attribute for that file descriptor, starting from wherever we are and adding the offset specified in the function call. So we're adding 100, which is going to be our current position at that time, plus 500, which is the offset we specified. So now, after the second call to seek, the position of our file is 600. Then we're going to write 100 bytes to that FD. So we're writing 100 more bytes of A. Okay, so all of the bytes between 200 and 599 in this case are going to be null because we just seeked from position 100 to 600, but there's nothing written from 200 to 600. So when we seek past the end of the file, those bytes are actually going to just be null. Now I'm skipping over the previous example and looking at this slide. What does the following program print? So what happens? We open the file out.txt, print the last digit of pi, we flush whatever's in our high-level user level buffer to standard out, and then we have a call to dupe2, which is going to redirect the file descriptor 1 to point to the file description corresponding to new FD. So we're redirecting our standard out to be out.txt and then printing 5. So print, instead of going to standard out, is now going to go to the redirected standard out, which is out.txt, and print 5. So in this case, it's not actually printing 5 to standard out, it's writing 5 to out.txt. And then we exit the program. Okay. So another thing I didn't mention is that the low-level API is not guaranteed to always read or write the specified number of bytes that you pass in. So if you're trying to read some number of bytes with a low-level API or write some number of bytes, you may have to do that in a while loop and keep track each iteration of how many bytes you read or wrote. And with the high-level API, it will basically internally execute this while loop for you so that you don't have to keep reading and writing with a low-level API in a while loop. So that's another advantage of the high-level API. It does this while loop iteration for you instead of necessitating you to do it yourself. Specifically, the low-level API can do this due to some asynchronous I/O interface. So some I/O resources don't immediately return back the number of bytes that you're requesting. And so you may need to keep looping to wait for those number of bytes to actually be read or written, as I mentioned previously.